Welcome to Pre-Calculus. Today we will investigate end behavior of functions, focusing on what happens to a function's y value as its x value approaches negative infinity or positive infinity. Let's take a look at two examples. We'll have a total of 4 examples for this section. We'll see 2 examples to begin. So we've got a function here, f of x equals 1/2 times base 4 to the power of x. We want to graph the function by creating a table of coordinate points. And then we want to determine the end behavior of the function as x approaches negative infinity and as x approaches infinity. Let's start with a table of coordinate pairs. We'll put our x column here on the left, and I'm going to record that as -2 through +2. Those are our traditional 5 x values. We choose those because they're centered around the origin. And we want to calculate f of x, our y value, which depends on x, and we're going to find it by plugging it into this rule. So we'll start with f at -2. So I'm just going to replace any x I see with the value -2. So this is 1/2 times 4 to the power of -2. And we'll evaluate this. Remember that the negative exponent flips over the base. So if you think of that as 4 over 1, 4 to the power of -2 is 1 over 4 to the power of +2. And then I'm going to distribute that power of 2 to the numerator and the denominator. So this becomes 1/2 times 1 squared over 4 squared, which is 1 times 1 times 1, 1, over 2 times 4 squared is 16 is 32. Now as a decimal, 1 over 32 is 0. Let's squeeze this screen down so we got some room. 0.03125. All right, so that gives us our first coordinate pair, -2, 0.03125. We'll keep going. So f at -1 is 1/2 times 4 to the power of -1, which again is 1/2 times 1 over 4 to the power of +1. We don't have to do a lot of work with the power of 1. Remember, that's the identity element for the exponent. It gives us back the base as is. So this is 1/2 times 1/4, which is 1 times 1, or 1 over 2 times 4, or 8, which has the value of 0.125. That gives us a second coordinate point, -1, 0.125. Now we'll calculate f at 0. That's 1/2 times 4 to the power of 0. And remember, anything to the power of 0 equals 1. So this is 1/2 times 1, which is 1/2, which has a value of 0.5. Notice as we go and get into the positive integers, the evaluation becomes a little easier. F at 1 is 1/2 times 4 to the power of 1, which is 1/2 times 4 over 1, which is 1 times 4 is 4 over 2 times 1 is 2. 4 divided by 2 is 2. Fourth coordinate point is 1, 2. Our last x value is 2, so let's evaluate f at 2. That's 1/2 times 4 to the power of 2. 4 squared is 16. And 1/2 times 16 over 1 is 16 over 2, which is 8. And that gives us sufficient coordinate points to put a framework for this function. So at -2, we're right above the x-axis, almost on the x-axis. At 1, we're not far off of it. At 0, we're at 1/2. At 1, we're at 2. So I'm just using these coordinate points to plot these values. And at 2, we're all the way up at positive 8. Now, recall with an exponential function, we have an asymptote at the x-axis. So within that framework, excuse me, I want to sketch that graph. So the graph starts over here in quadrant 2, but very close to the x-axis, hits these points that we've plotted, and then just explodes with that exponential growth as x gets bigger. So that completes the first task. We've graphed the function with a table of coordinate values. And now we want to determine the end behavior of the function as, first of all, x gets closer to negative infinity, and also separately as x get closer to positive infinity. Let's consider that first one. As x approaches negative infinity, so I'm going to indicate on the graph where is negative infinity. That's the left-hand side of the graph. So as x approaches negative infinity, we have to ask ourselves, what happens to the y value? Well, we can see based on the asymptote that we dashed in on the x-axis, the y value approaches 0. And you can kind of see that in our y values as we got farther away from 0 in this direction. Negative infinity is this direction on the table. Those y values are getting smaller and smaller and smaller towards 0. The second consideration that we want to analyze is what happens to the y values as x gets close to positive infinity. So as x approaches positive infinity, y approaches what? So positive infinity is out here to the right. And if we look at our y values on our table, they really get bigger and bigger and bigger. In fact, if I were to zoom down to 10, let's say we tried to evaluate x value of 10, f at 10 would be half times 4 to the power of 10. And that calculation gives us the value of 524,288, which is extremely ungraphable. That's way up past the ceiling of the room. So what that indicates to me is that if I take x even past 10 out to infinity, the y value is going to explode forever and forever and forever, and y is going to approach positive infinity itself. And that completes our initial task here. We've graphed the function, and then we analyzed it for end behavior. What happens to the y as x goes to negative infinity? What happens to the y as x goes to positive infinity? Let's look at one more example. So here we've got a logarithmic function. Same task, we want to graph from a coordinate table. And we also want to analyze for what happens to the y as x gets closer and closer to the left. What happens to y as x goes closer and closer to the right towards positive infinity? Well, let's graph the function first. And let's choose our traditional -2 through, we'll go through 3 for this one. 0, 1, 2. I'm going to put a value here, e, and 3. Now, I include that e because this is specifically about the number e. So just to fill in again, e has the value of about 2.718. That's an approximate value. E is an irrational number that goes on forever without repeating. So that's why I use the wavy equals sign. Now the reason I say that value of e is because the natural log of x, which we say ln x from the French logarithm naturel, is equivalent to log base e of x. Now, as I look at my table here, there's only 2 of these that I can evaluate directly by hand. Let's pick those out. So I'm going to pick up this first one at 1. So I can calculate f at 1 is the natural log. I'm going to write it as log base e of 1. And recall how a logarithm works in terms of evaluating. It starts with the base. We're going to convert it to an exponential. So this is equivalent to e to some power of y, which I don't know. That's my evaluation, would equal the argument 1. So it's kind of a clockwise circle there. You start with the base to the y value, back to the argument, the x value. The reason I've chosen this one is because we're asking e to what power would equal 1. Well, anything to some power will equal 1, and that power is 0. So at 1, the function has the value of 0. Now the other value that I can calculate here is e. So f at e is log base e. Again, I'm using that expanded form so that we can see what's the base on ln, natural logarithm, of e. Now, to convert this to an exponential, we'd start at the base, so e to the power of some y, I don't know, what is it, equals e. Well, anything to the power of 1 equals itself, so this evaluates as 1. So these 2 coordinate points we can evaluate manually. So this is 1, 0. We can plot that on the graph, and also e, 1, which is also plottable, but we got to estimate 2.718 is about there, and we're going to go up 1. Now, the rest of the values we can't calculate very well. We can do some stuff with the first 3, but let's use our graphing calculator to help. So I'm going to head over to Desmos. And I'm going to type in that function, f of x equals, and I can grab, if I go down to the keypad and expand it, and select the functions button over here to the far right, natural logarithms in the miscellaneous tab, ln of x, and I'm going to disable the keypad and create an edit list, convert it to a table. So we've got some values. We see we have the one that we had graphed. Let's go ahead and type in e, see if we had calculated that correctly. Looks so. And 3. So notice for these -2, -1, and 0, that's because I can't raise e to the power of any number and get a negative value. We saw that with our previous exponential function. You cannot raise some number to a power and get a negative number. So those are showing up as undefined, undefined, undefined. And then I'm going to record these 2 values we did not calculate. So at 2, we've got the value of 0.693. And at 3, we got the value of 1.099. We'll head back to our notes screen to graph those. In fact, we'll fill in our table first. So for -2, that was undefined. -1 and 0 also undefined. In terms of the graph, that just means there's no graph at those points. 2 had the output of 0.693. I can plot that. That's roughly there, just above 1. And then 3 had the output of 1.099. And let's graph that. we saw from the graph that we generated on Desmos that there was a vertical asymptote on the y-axis. So when I go to plot this function, it starts to the right of the y-axis, and as it gets higher above the x-axis, it veers off to the right. And that is the graph for natural log of x. This is the natural logarithm of x. Guys, the reason why we say ln is from the French, which switches these words. It's like our Spanish language. It flips adjectives and nouns, so logarithm natural, ln. Now, that completes that first task. We do need to say what happens for the end behavior as x approaches. I'm going to put negative infinity, but it's almost unhelpful for us to think about negative infinity because the graph does not exist in quadrants 2 and 3. We saw that those x values had undefined y values. So I'm not going to say as x approaches negative infinity. I'm going to say what happens to the y value as x approaches 0, the y-axis. So as x approaches 0, y approaches. And what we're looking at is this tail end of the graph that is rooted down in between quadrants 3 and 4, right in quadrant 4 actually. Now, if we think about the y value as it's dropping like that, it's going forever, and that's becoming negative infinity. So for this function, as x approaches 0, the graph has a function value of y approaching negative infinity. The last part of our task is as x approaches positive infinity, y approaches something. Well, let's go to Desmos to see if we can use that feature to decide what's happening to the function as the x value gets very large. So I'm going to type in 1,000. So that's way off the graph. It's not showing up. Our graph only goes to 10 here on the right. So 1,000 would be 100 times as much. And it's only up at 6.91 roughly. If I go to 10,000, it's up to 9. If I go to 100,000, it's up to 11.5. A million, 13.8. 10 million, 16. 100 million, 18. So although as the x value gets really, really large, the y value doesn't rise a whole lot, but it never stops. If I go to another 0, it goes up, another 0, it goes up. There's no limit. So although the growth in the y is small relative to the growth in the x, we have to conclude that as x approaches positive infinity, y also approaches positive infinity. It keeps going up as it goes to the right. And that completes both the graph and the analysis for end behavior for this natural log of x. We'll pause right here, give you a chance to go work on some of these questions, and we'll come back with 2 final examples describing the end behavior of functions. Thank you for joining. See you in a moment.